Let's look at 5.9 where we have the matrix 1, 2, 2, 4. See what happens on this one. We're going to follow the same procedure as the other two. Maybe we'll go a little bit quicker to begin with. So we just take the determinant of a minus lambda I, which in this case is the determinant of 1 minus lambda, 2, 2, and 4 minus lambda. Okay, and then we go through this and see what we get. We get 1 minus lambda times 4 minus lambda, and it looks like minus, and we'll multiply those together, it looks like we get minus 4. Okay, so, and this is all equal to 0 because we want these determinants to always equal 0. So now we set this out, and we get 1 times 4 is 4, and then we've got 4 minus 4 lambda minus lambda plus lambda squared minus 4 equals 0. And so if you look, oh hey look, those cancel, and it looks like I got lambda squared minus 5 lambda is equal to 0. Lambda minus 5 equals 0, and so either lambda equals 0 or lambda equals 5. So those were the two options that we get. Now let's look really quickly and kind of see what happens. See what happens on this one. So first I want to point out something interesting. Notice lambda equals 0 showed up as an eigenvalue. What do you notice about this matrix to begin with? Well, what I notice about the matrix is that row 2 is a multiple of row 1. And so if I were to row reduce this one already is a non-invertible matrix. It was non-invertible, and so 0 was an eigenvalue. But that means that you can come up with a determinant of 0 without changing the numbers at all. So let's make a quick point. And it is that 0, lambda equals 0, is an eigenvector. Sorry, that's supposed to be the word eigenvector. If and only if A is not invertible. So what does that mean? So that means that we now have another thing to add to our list. So we have those list of lots and lots of those lists of all the items that mean the same thing. If you look at your notes, you'll see on page 53, I've now added one more item. I've added T. So what's the same as being an invertible matrix? If it's invertible, it's row equivalent to the identity. It has in pivot positions. You have things like the columns span R. You have things like the rank is in. You have all these things are all the same. Finally, the determinant is not 0, and then the last thing you have is that 0 is not an eigenvector. So this is the last one. So this adds T. This isn't the last one in existence, but it's the last one we're going to see this semester. So our final version, we have T items that all mean the exact same thing. So there you go. Okay, let's now tackle this. We've got the lambda equals 0, lambda equals 5. Let's look at each of these eigenvectors one at a time and see if we can figure out its associated eigenvalue and make sense of those. Okay, so let's start with the lambda equal to 0 eigenvector. Well, that's simple. You don't even have to subtract anything. So that means we're just taking 1, 2, 2, 4, 0, 0, and we're just simplifying that, and that simplifies to 1, 2, 0, 0, 0, 0. Sorry, I'm squishing on this piece of paper here. I'm feeling really lazy after I've been doing all of these. Okay, so we get 1, 2, 0, 0. So what does that mean? That means x plus 2y equals 0, or x equals negative 2y. And so our solution for our eigenvector, so when we have an eigenvalue of 0, our solution is the eigenvector negative 2, 1 times y. So when our eigenvalue is 0, we get negative 2, 1. You'll notice that works if you try it out. In fact, it makes each of these equal to 0. So if you use this vector and multiply it by this, you get 0 every time. Okay, now let's do the lambda equals 5, and maybe that one will be a little bit more interesting. I'm not sure that it will. Let's see. So if we do lambda equal 5, then we get 1 minus 5 is negative 4 and 2, and then 4 minus 5 is negative 1. And so now we need to row reduce this. Let's put these equal to with zeros here. And let's row reduce this. Well, the first row reduction, this and this cancel. And so we get -4, 2, 0, 0, 0, 0. And then I should row reduce that. I'm going to do this a little bit different. What if I make this equal to 1? So what if I make it -2, 1, 0, 0, 0, 0. And then I can use the fact that -2x plus y equals 0. And I can just do y equal to -2x. Maybe I'll make x my free variable instead of y. It does, you know, we've kind of seen earlier in the semester, we have some flexibility in how we choose things. And that will make my xy vector look like this. So now my xy vector will be a multiple of x. X is equal to x, and y is equal to -2x. And so we get the vector 1, -2. By the way, if you had done it a little bit different, you should have gotten a vector that's the same as 1, -2, except multiplied by something. So maybe -1, +2, or -2, +4, or 2, -4, but you know, or something like that. But hopefully it was kind of similar to this. Maybe 1/2 -1 was something like that. Okay. Well, hopefully that went well. I've made a decision as I went through these. 510 is a good one, but it's a little long, and I kind of don't feel like doing it. So I'm going to skip 510 and go straight to 511. So if you want to do that as well, good luck. That's perfectly fine. If you want to do 510 on your own and work on it, that's fine also.